As you interact with the air surrounding you, you affect its movement, and it in turn affects you. However, at the moment, and perhaps even for the rest of eternity, we are unable to make exact, deterministic, or statistical predictions for its movement because of the beautiful yet chaotic movement of turbulent flow. And therefore, exactly how a fluid affects you is also undeterminable. Nonetheless, we are able to make broad stroke observations of this reciprocal relationship between object and fluid, allowing us to harness the power of fluids for our benefit. For example, let us take this curved plate that is moving through a fluid. Say we follow a particle as it moves past the plate and trace its path. We will see that the closer it is to the plate, the more it is bent to the plate's shape. These paths are called streamlines. And just as you feel a force from your car as you negotiate a corner, a streamline that is curved means that there is some centripetal force directed towards the center. A fluid feels a force when the pressure on one side is greater than the other. Therefore, the centripetal force that we see on the curve must be because there is higher pressure outside the curve and lower pressure inside the curve. This means that the pressure must be dropping in the direction of the center of the curvature. Going back to our curved plate, say we pick a point high above and undisturbed by the plate and call it point A. Then the pressure there is at atmospheric pressure. Now let us pick a point on the plate at its crest and call it B. And as we move from point A to point B, we note that the streamlines are becoming more and more curved and therefore have a greater pressure drop until we arrive at point B. This means that the pressure at B is less than atmospheric pressure at point A. Now let's say we pick a point far below and again undisturbed by the plate and call it point C. And again move towards the bottom of the plate now at point D. And notice that there is an increasing pressure gradient, since the pressure again here must be dropping in the direction of the center of the curvature. This means that the pressure at D is greater than the atmospheric pressure at C. Therefore, it must be true that the pressure at B above the plate is lower than the pressure at D below the plate. This difference in pressure on the two sides of the plate generates an upwards force on the plate. This is what we call lift. And this principle of lift is what has allowed us to build many things, from fans for fresh cool air, to sailboats moving against the wind, to turbines generating electricity, and to airplanes soaring high above the sky. The cross-section of a lifting body is called an airfoil, and is most common as a teardrop shape, round at the front leading edge and sharp at the rear trailing edge, which is more efficient than a simple curved plate for flight. A symmetric teardrop shape will actually produce no lift, as it has the same streamlines above and below the airfoil. By changing its angle of attack, or the angle it makes with the airstream, we can create different streamlines on each side, and therefore lift. Further, since we're moving it through a medium, there is something called drag, which costs energy to overcome. One source of drag that we will focus on is called pressure drag. As we follow a fluid along an airfoil, it'll contract until it reaches the crest and start expanding thereafter. The expanding fluid, from conservation of mass flow rate, will slow down. This, by Bernoulli's principle, means the pressure increases. The layer of fluid that usually hugs the body's curvature is called the boundary layer and is already slowed down by friction with the body. But because of this increasing pressure gradient that the fluid near the airfoil is also fighting against, it begins to slow down even more until it starts moving backwards, and the boundary layer separates from the body, creating a bubble of recirculating flow that has drastically less lift, as it is no longer changing the flow's direction directly above the airfoil, and causes much more drag as well, as the pressure in the rear decreases drastically. since the energy that is usually used for pressure is used to generate turbulent eddies, allowing the pressure in the front to create a resultant rearward force. This effect increases as angle of attack increases as the flow expands more, increasing the pressure gradient, making the boundary layer separate earlier along the airfoil. And how do we know this? One way we can see these effects is, of course, through experimentation. So that's what I did. I went to the University of Southampton to conduct what is known as particle image velocimetry, or PIV, on an airfoil to see these effects in action. This method involves dispersing tiny reflective particles into a water tunnel, which is a tunnel that keeps water flowing at a certain speed, and putting an airfoil model in it. Then, using different lenses, we spread a laser into a thin sheet and set it pointing through the water tunnel, which illuminates the particles passing through that laser sheet. The light scattered by the particles is picked up by a high-speed digital camera, taking 120 pictures every second. All these images are then read by some software, which basically slices two consecutive frames into small interrogation zones and cross-correlates the two frames with some fancy statistics to determine the amount it has traveled and the direction it has traveled over the two frames. Inputting the time difference between the two frames allows us to obtain a velocity. Doing this over the whole laser sheet will give us a field of instantaneous velocities surrounding the airfoil. And this is what we get. Here is an airfoil at 5-degree angle of attack. The white areas represent the airfoil itself, and shadow regions with not enough particles visible in the image, and a mount that is a straight line you see over there. And the speed is displayed as a fraction of the speed of the flow without any object present, with red being the fastest and blue being the slowest. Despite the flickering, we can immediately see that the flow above the crest of the airfoil is generally higher than the flow below the airfoil. And by Bernoulli's principle, this means that the pressure above is lower than the pressure below, meaning there is lift. We can even take the average of all the instantaneous velocities and see the bending of the streamlines downwards that again signifies lift. Of course, it is impossible to ignore the blue recirculation bubble in the rear. That is where, as mentioned before, the flow starts slowing down, sometimes going backwards, causing the boundary layer to separate instead of hugging the body. This means more pressure drag and a loss of lift. But don't be alarmed, this usually doesn't happen in normal flight at 5 degrees angle of attack, as this experiment was done in what is known as low chord-based Reynolds number. The Reynolds number is defined by the density of the fluid multiplied by the free stream velocity and the chord length, or the length of the airfoil from tip to end, and is divided by viscosity of the fluid. This measures the ratio between inertial and viscous forces, and the relatively slow speed of the water tunnel, and therefore low inertial forces compared to the viscous forces, means that there is even less energy to combat the pressure gradient, unlike usual flight. We can even see that this slow blue recirculating bubble increases in size as we increase the angle of attack. Here it is at 10 degrees and at 15 degrees. At 15 degrees, this slow moving recirculating bubble is so large the amount of lift has likely been drastically compromised. This is evident when we look at the average velocities and the streamlines and see that they don't curve down near the crest, but rather way behind the crest and high above the airfoil. This loss of lift from this giant recirculation zone is known as stall, which can happen in normal flight, albeit very rarely, but you absolutely do not want this to happen, although pilots are well trained in the event that it does occur. That aside, from this recirculation bubble arises beautiful vortices that are tumbling around it, and what I consider one of the most beautiful phenomena in the universe. The seemingly random movements of chaotic turbulent flow in the interfaces between slow-moving flow and fast-moving flow is why, Unlike the other areas of physics, we don't actually have models that can deterministically or statistically predict the movement of fluids. This unresolved wonder is what makes the study of fluids a buoyant puzzle with many fascinating phenomena yet to be discovered. So, I urge you, perhaps the next time you get a window seat on a plane, or even the next time you run your hand through a pool of water, take a closer look. What interesting things do you see?